Hello friends, you are welcome to my new series called Embedded Design in Electrical Power Domain. Most of the embedded design engineers come from electronics background. So to some extent, they lack the knowledge of a variety of electrical concepts and parameters that makes them uncomfortable in this environment. Once this gap is filled up, they can deliver excellent designs. Purpose of this series is to fill up this gap. Even guys with electrical background will benefit from this series as they will be able to relate electrical parameters with embedded concepts and start designing embedded things for their domain of electrical power. Let us start now. What is electrical power domain? I have given a sketch that briefly depicts the entire electrical power domain. It starts with a power plant and ends with the equipment we use. The large generating plants are generally far away from our towns. There may be thermal power plants located where the coal mines are. There may be hydel plants located close to rivers. There could be nuclear power plants, solar plants, and wind power plants. Picture gives just an example where power is generated with a voltage of 11 kV. Then the voltage is raised to 220 kV using a massive transformer, as you can see. This stage is called transmission stage. This takes power to your town. Then its voltage is brought back to 11 kV and power is distributed with the help of transformers in different areas of your town. These transformers bring the voltage down to 400 volts. This 400 volt is the line voltage, which amounts to a phase voltage of 230 volts. That is the voltage you get in your house. What is the equipment involved? As you can see a small picture, it shows some of things starting with a power plant, a substation, a transformer, AC and DC motors that are involved in the setup. This is just a small subset of what is in store for you. What is our job? Or to be specific, what is the job of an embedded design engineer? Our job is to take care of the whole setup from generation to your, that is, to end users' electrical equipment. What is the meaning of taking care? Taking care means number one, to monitor, number two, to control, and number three, to protect. What is that? Monitor, control, and protect. These are the three dimensions of taking care. And look, this is nothing new. I say this from a different point of view, from the point of view of a human being. All parents do this to their children. They monitor, control, and protect their children, right? These three actions must happen intelligently, continuously, and automatically. When you hear these three words, the first thing that comes to your mind is this is an appropriate place for deploying microcontroller, right? You are absolutely right that this is what I will like to go into for a embedded design. Yes. Go ahead and plan in detail to start. First, understand the meaning of these three terms: monitor, control, and protect. Two examples of monitors are shown in the picture. Namely, a multifunction meter and an alarm annunciator. Multifunction meters shows various parameters like three-phase voltage, currents, power factor, kilowatt, kVA, and so on and so forth. It is quite challenging. It is absolutely challenging, and you should know how to measure these quantities before you display them. Display is a simple thing for the embedded designers, but how to measure it, that is the critical issue. So it is challenging. About that there is no doubt. Now let us move to the next one. The next one is alarm annunciator. What is an alarm annunciator? This one. For the purpose of monitoring the state of equipment, almost every machine carries a switch that changes state when some specific parameter of the machine goes beyond desired level. Take the case of a machine for which upper and lower limits of supply voltage are specified. In such a machine, there are two relays. One relay trips when supply voltage exceeds upper limit, and the other trips when voltage falls below the lower limit. For some machine, it is the air pressure or fuel level or lubricating oil level or battery voltage limits, etc. that trip relays. There may be a combination of many such machines, each giving indication by operating relay contacts. Each one of these relays is connected to a lamp through an electronic circuit such that lamp starts flashing when the corresponding relay contact changes state. This electronic device is called alarm annunciator, which supports several relay contacts. Each lamp on it also provides a label that shows the cause of the problem, as you can see here. Like over voltage, under voltage, fuel level, temperature, and so on. And an alarm annunciator is located in the control room. An operator sitting there gets to know if there is any problem with any equipment. In fact, when lamp flashes, one alarm also goes up to attract the attention of the operator. On hearing the alarm, he looks at the panel to see which lamp is flashing, and its lesion tells him what is the cause. Then he takes a suitable action. There is a push button to silence the alarm. Annunciator has many other interesting features. We will go into depth when we set out to design annunciator. Now you see what is monitoring and how it is done. So the next actionable area is control. Let us have a look at control. I will start with two examples depicted in the center. One is load balancing relay and the other one is power factor controller. A load balancing relay is a controller used with multiple generators running in parallel. Basic idea is to ensure that generators running in parallel share the load in proportion to their capacities. Let us take an example. There are two generators. One is rated for 400 kVA and the other one is rated for 200 kVA. If the load is 300 kVA, then these generators should share the load in 400:200 proportion. This means that the bigger generator delivers 200 kVA and the smaller one 100 kVA. The important point is that this should happen automatically and continuously. Another important point is you should know what parameter of the engine needs to be controlled to bring about this kVA sharing control. And yes, another point, you should know how to control that set of parameters with your embedded device. With a load balancing relay, we achieve this function automatically and continuously. This picture shows the load balancing relay and, for example, two gensets. The load balancing relay controls both of the gensets and ensures that they share the load in proportion to their capacities. To sense the load, it reads voltage and currents, and its built-in intelligence decides how to control the two generators such that they deliver a proportionate power. For example, here 400 kVA and 200 kVA are the two generators. Load is 300 kVA. So the bigger one delivers 200 and lower one delivers 100 kVA. So that is how the load balancing happens. The next example is a power factor controller. Power is equal to VI cos phi. For a given power, higher the power factor, lower is the current drawn from the power line. So if you are running a factory with a low power factor, you are unduly loading the transformer that supplies power to you. So power supply company claims a fine on you for poor power factor, and that is where PF controller comes into picture. The PF controller is a device that continuously monitors power factor, and if it falls below a predefined level, it connects one capacitor to the power line, as you can see. If PF continues to be below acceptable level, then it connects one more capacitor to the line. In this way, it goes on adding capacitors until PF is at acceptable level. It does this step by step to ensure that power factor does not become leading. Power factor must remain lagging. So it may have to disconnect some capacitors sometimes. A leading PF raises line voltage and puts all connected devices at risk. Hence, the step-by-step method. The third type of embedded design activity relates to protection. Monitoring is required to be able to protect. So, monitoring is built in an overcurrent relay or any other protective relay. The most common protection is overcurrent protection. There is a variety of protective relays, for example, feeder protection, motor protection, transformer protection, current protection, voltage protection, generator protection, and so on. There is a huge list and it is very challenging. We will be spending a lot of time on design aspects of a large variety of relays. So friends, be prepared for the hard work that is in store for you in the time to follow. See you in the next episode. Thank you.